Hi everyone. In this video we are going to go through the answers to the studying assignment for our quiz on 3.2 and 3.3. Just a note, you can use your calculators. Make sure you show all your work. You need to know the Pythagorean identity. You're not going to need to know any integrals or anything from a table other than the two identities that I've given you on this assignment. And you also do need to know the correct trig substitution depending on what the scenario, depending on what you see in the integral. And in our first problem, we are integrating tangent to the fourth x, secant to the fourth x. So you want to take and look at your exponents. Do I want to make my u substitution u equals tangent to x or u equals secant to x? And the correct answer, because we have secant to the fourth, our secant is to an even power. We're going to set u equal to tan x, tangent x, because then du is equal to secant squared x dx. So I'm going to break off a secant squared and save that for the du term. And the other two secants we're going to write in terms of tangent. And so what it looks like after our first, after we break things apart, this is equal to the integral of tangent to the fourth x times secant squared x times secant squared x dx. So then this secant squared, we're going to write in terms of tangent. Secant squared is 1 plus tangent squared x. So then we get the integral of tangent to the fourth x times 1 plus tangent squared x secant squared x dx. This is u. This is u. Well, the first one is u to the fourth. The second one is u to the second. And all of that is my du. So this becomes u to the fourth, 1 plus u squared du. Now, don't make a mistake here. Don't start taking your antiderivative yet. We need to distribute that u to the fourth in. When do we get u to the, not u to the fifth. We get u to the fourth plus u to the sixth, the integral of that in terms of u. And then finally, well, almost finally, u to the fifth over 5, u to the seventh over 7, plus our constant c, and then we're going to back substitute. U was tangent to the fifth x over 5, plus tangent to the seventh x over 7, plus our constant c. Moving on down to number 2. All right, we have cosine to the fifth of 2x times sine squared of 2x. We see that odd exponent on the cosine, and that's the one we're going to save for the du. So this becomes the integral 0 to pi over 4 cosine to the fourth 2x times, I'll put my times in there, sine squared 2x cosine 2x dx. And then our u is the sine of x, not the sine of x, the sine of 2x, and then du is 2 times the cosine of 2x dx. And so we can see in our integral right there is our cosine 2x. That's our du, but we don't have the 2 there, so we're going to factor a 1/2 out in front of our integral when we make that substitution. Right here, the cosine to the fourth, since our u is in sines, this is 1 minus sine squared 2x squared. All right, so let's see if we can make our substitution here. I'll come back to the bounds in just a moment. Let's see, we have 1 minus u squared squared. That's the parentheses part. Then this guy here is just a regular u squared. And then the cosine 2x dx is just du over 2. So I'll pull my 1/2 out in front now. All right, what about those bounds, top bound and bottom bound? Well, let's go back to our substitution. The sine of 2 times 0, or the sine of 0, is 0. And then the top bound, the sine of 2 times pi over 4 is pi over 2. The sine of 90 degrees is 1. So our u-bounds, our new bounds, our u-bounds is 0 to 1. Our next step is to simplify this algebra. I'm going to square what's in the parentheses, but I'm just going to put it below it. 1 minus 2u squared plus u to the fourth. And then I'm going to rewrite my integral as 1/2 integral from 0 to 1. And let's distribute that u squared in. U to the second minus 2u to the 4th plus u to the 6th du. Okay, I'm running a little bit low on space here, but I'll just keep going over to the right. Then that is equal to, let's take our antiderivative now, so 1/2 out in front, u to the 3rd over 3 minus 2u to the 5th over 5 plus u to the 7th over 7. And then we're going to evaluate that over the bounds from 0 to 1. And let's move over a bit more. And what do we get when we plug in our top bound? Let's see, 1/2 times 1/3, because 1 cubed is 1, minus 2/5, because 1 to the 5th power, still 1, plus 1/7, because, well, 1 to the 7th power is 7. There we go. And then the bottom bound is 0. Right? Check it in each term. You should get 0. And then we'll just use our calculators if you want to combine those three fractions together. And when you do that, inside of the parentheses, you get 8 over 105. Multiply that by 1/2, you get 4 over 105. All right, and that's answer to number 2. Let's move on down to number 3. In this one, we just have to integrate cosine squared, which when we have cosine to an even power and no sine to an odd power, that's the case where we need to use one of these identities. And I'm just seeing now that I have a typo there, right? That should be the sine squared of theta. I don't know how I did that, but they both say cosine squared. They can't both possibly be cosine squared. So now that we've corrected that, let's go back to the integral. We're integrating cosine cubed 3x. So for this one, we are going to use the top identity and make a substitution into our integral. So in that integral, we have cosine squared 3x is equal to, I'm going to pull the 1/2 all the way out in front, and then it's 1 plus the cosine of 2 theta. And in this one, in my integral, the theta is 3x. So if you knew that that should be 6x, pat yourself on the back there. 1 plus the cosine of 2 times 3x, and then dx. Okay, let's make this our 6x, and then take our antiderivative. 1/2 times x. The antiderivative of cosine is sine, so we have the sine of 6x divided by 6 plus our constant c. You could leave the 1/2 out in front of the parentheses. You can distribute it in. I'm going to leave my answer just like that. Now we come to these examples on trig substitution. Take a look at number 4 here. The first thing to see inside of that integral is the square root of x squared plus 25. So in that, when we see that inside of our integral, that addition, we're going to say x is equal to a, which in this case is 5, times the tangent of theta, and then dx is equal to 5 times secant squared theta d theta. We can also draw our reference triangle. Theta goes down there. There's my right angle. And I'm looking at this equation. Tangent theta is opposite over adjacent, x over 5. And then I put the square root on the hypotenuse, like that. All right, so that's our preliminary work. Now we'll go back and make the substitution. Up in the numerator, we have x cubed, so that would be 125 tangent cubed theta divided by the square root of 25 tangent squared theta plus 25. And then my dx is after the parentheses, so 5 secant squared theta d theta. There's our first big ugly step. Okay, so let's take a look at that square root in the denominator. We can factor the 25 times tangent squared theta plus 1, like that. That's not a fraction, that's just drawing a line. And then the square root of 25 is 5. Tangent squared theta plus 1 is secant squared, and we take the square root of that, and that denominator simplifies to 5 secant theta. Okay, so let's substitute that into our integral now. 125 tangent cubed theta over 5 secant theta times 5 secant squared theta d theta. Do a little cancellation. That 5 secant with that 5 and one of those secants. And our simplified integral now says the integral of 125 tangent cubed theta secant theta d theta. Well, now we need to use the techniques of the previous couple examples and figure out how do we do a little u substitution on this trig substitution to take our antiderivative. And that's why I said it's a little bit more challenging than I would put in a quiz. I'm not going to make you do techniques from 3.2 and 3.3 in the same problem. So right now it's more practice from 3.2, but don't expect to have to do this in the same problem, these two things in the same problem. Okay, so for this one, I'm going to say that u is equal to secant theta because du is secant theta tan theta d theta. So I'm going to save one of those tangents and write the other two in terms of secants. And you'll see what that looks like. 125 tangent squared theta. And then we write it in this order. Secant theta tan theta d theta. All of that is my du. And then tangent squared, we're going to write that as secant squared theta minus 1. Okay, so let's see. Can I make my substitution now? Yeah, let's say this is equal to, forgot my equal signs along the way. This is equal to 125. I could have pulled that 125 out at any point. I'm doing it now. Times the integral of u squared minus 1 du. Whoa, where did everything go? Everything underlined in black is the du. The tangent squared, we use the identity. And then secant squared theta minus 1 is u squared minus 1. That antiderivative, not bad. Parentheses u cubed over 3 minus u. And then we have two layers of back substituting here. The first layer is u is equal to secant theta. So, oops, well, let me get my 125 times secant cubed theta over 3 minus secant theta. So there's my first layer of back substitution. All right, and then our next step is to go in terms of x. Oop, and I should have put my plus c. Let me add that in. Plus a constant c here, plus a constant c there. All right, now let's go and rewrite our answer in terms of x. Well, I know that the cosine of x is adjacent 5 over hypotenuse is the radical. So if I'm writing secant, if I'm substituting secant, I'm just going to flip that fraction over. So let's see how this goes. 125 parentheses 1/3, and then secant, I'm again flipping it over. So I'm going to put in parentheses square root of x squared plus 25 over 5 raised to the 3rd power minus that same thing, x squared plus 25 over 5, close that parentheses, plus a constant c. And, well, that looks like a big hot mess. We could probably simplify a bit there. When I distribute this 125 to the first term, do you see how there's going to be a little 125 in the denominator there? It'll cancel out. And when I distribute it to the second term way over there with a giant loopy arc, the 5 will cancel. So I guess I could write this a little bit simpler as, let's see, the square root of x squared plus 25 cubed over 3, so I'm putting that 3 back in the denominator, minus 25 radical x squared plus 25, and then plus the c. I think that's about the best I can get this one. Okay, that was pretty involved, but hopefully you could follow along or rewind the video, watch a couple of the steps again, and see if you can figure out where they came from. All right, now we have our last one. This one is actually not as terrible as that previous problem, but it should be familiar, actually. If you recall from earlier in the semester, this antiderivative is inverse sine of x. We got it using a specific process. We derived where that formula came from, but now we're going to show that we actually get the same result using a trig substitution. When you look inside of that integral, you see the square root of 1 minus x squared. And so that tells me that I'm going to set x equal to a is 1 times the sine of theta, and dx is cos theta d theta. When I draw my reference triangle, theta's down there. That's kind of a theta. There's my right angle. Sine theta is opposite, come on, I can't write today, over hypotenuse. So that's x over 1. And then the radical goes on the other leg, like that. So there we have our reference triangle and our trig substitution. So let's plug in that trig substitution. And we go the integral of 1 over the square root of 1 minus sine squared theta. And then dx is cos theta d theta. There we go. Now let's simplify under the radical. 1 minus sine squared theta. Make that substitution. 1 over the square root of cosine squared theta times cos theta d theta. Well, in the denominator, the square root of cosine squared is just 1 over cosine theta times cosine theta d theta. See how much more direct this one is to simplify? Oh, and hey, my cosines cancel out. Cosine there, cosine there. So what am I really integrating? This is the antiderivative of 1 d theta. You could even just write that as integral d theta, right? All we have is our constant of 1 in there, and when you take the antiderivative of a constant, you get a constant times x in x terms, but in this problem, they're thetas, so this antiderivative here is theta plus c. So that's a little bit weird. All we have for our integral is theta when we're done taking the antiderivative. Okay, so what does the back substitution look like? Well, I don't need my reference triangle for this one because I already have theta written down right there. If x is the sine of theta, then solving for theta is the inverse sine of x. So when we back substitute, inverse sine x plus our constant c. And hey, we got the same thing that we derived earlier in the semester, which, well, we should because it's the same integral. All right, hopefully that review helps as you prepare for the quiz tomorrow. I know these topics can be pretty challenging, which is why I'm giving you the extra study tool as you prepare, and I hope that it is beneficial to you. Please let me know if you have any questions, and I will see you in class.